Good afternoon, this is Schweitzer. We're going to run through some smart notes on atomic structure. Now, there are lots of resources available. This is just one of them. You'll find in your workbook. Typically, there'll be more than one posted video. This one just walks through and has some stuff to fill in. So, these are our standards. This is standard 2-1, and there's a few different versions, variations of it as we move along. But subatomic particles. All right, so again, some of you know a lot of this information already, and we're just going to be filling in some of the gaps, hopefully reinforcing a few things here. All right, so name. All right, so we got a proton. We have the mass, which is 1 AMU, charge of +1. We have a neutron, which is 1 AMU and would be no charge. And we have an electron, which is approximately no mass and charge of -1. So AMU stands for atomic mass unit. And you could actually convert that to a kilogram. So it's just another unit. You can convert it to a pound. It's just a unit of mass. And it's a mass unit of mass measuring small things. Okay. So that being said, all the mass is located in the center of the nucleus, okay? And electrons are located on the outside. So with that, a few things that we might want to do with it, okay? So what does an atom look like? Now again, anything that doesn't have a box around it is assuming that it's not in your workbook. So with that being said, all right, this is called the Ernest Rutherford experiment, and he essentially shot alpha particles, which have mass, right? And they hit things, and I think he kind of expected everything to go through, but he realized that a lot of it went through. But he got some ricochets sideways, some came right back, which gave him the idea that there was really this hard center here, and he got a Nobel Prize in chemistry, yet he's a physicist, so that kind of dumbfounded him. But either way, so center with lots of air around the outside. So, all right, atomic number. What do you want to know about atomic number? This is the number of protons. Okay. Now, this is something that isn't really all that big of a deal, but it's important. The key idea here is that the periodic table is actually ordered by protons. So the number of protons determines the element. And when I say the periodic table is ordered by them, then what I'm saying here is that essentially every time we slide over one spot on the periodic table from here to here, the only difference from here to here is one proton. All right. So in this situation here, we have a mass number. This is essentially the total mass of an atom. And because of the units of AMUs, it's the protons plus the neutrons will equal the total mass. Total mass for a given atom. Okay. So here in this picture here, you'll note that we have a situation where, let's say, color-wise, we see the blue ones are the protons. Okay, so this has got 2 protons, and there are 2 of them, and then there are 2. I shouldn't say that. There's little charges on there. So these are the protons, and these are the neutrons. It doesn't matter at this point. Neutrons, protons. These will be positive. These will be negative. Okay. So this is helium. This is how we would show this. Okay. Helium is several notations you could use on this. Okay. But this is the atomic number, and this is the mass number. Okay. And you'll note that what does this mean? Okay, this notation, another one of these notations. We should be aware that this number right here is the mass number. Wouldn't do much good to have the atomic number there, because the element is determining that. So if I would say carbon 13, what am I referring to? Okay, so at this point I'm referring to the fact that this element is carbon. So how many protons does a carbon atom have? We go up to find carbon, and I'll say carbon's got 6. And then the total of the protons plus the neutrons will equal 13. And therefore, this thing has what? 7 neutrons. Okay, kind of an unstable form of carbon that radioactivity decomposes, and they can measure how old things are based on radioactive carbon dating using carbon-13. All right, but that's another story. All right, so moving along here. All right, so all right, again, carbon-13, carbon-14, 12, carbon-13, 14. So these are all different isotopes of carbon. All right, so in this case, what do we got here? So we have this thing called average atomic mass. So now, again, this one's not on your sheet here, so but let's add in a few notes here just as we move along. What's an isotope? Okay, this means you have the same element, but different, okay, mass. Okay, different mass. Now, what does that mean? It means you have the same number of protons. Protons are the same, and the number of neutrons is different. Okay, so this is a pretty important chart here, because now mass numbers are fine, let's say carbon-14, okay? You'll never find carbon-14 on the periodic table. You're never going to find the mass number on the periodic table. So what is on the periodic table? What's on the periodic table is our average mass. Okay, now if you were only grabbing 5 or 6 carbon atoms, then the average probably wouldn't do you very good, because you could have just by chance have all 12s, or you could have a couple 13s or 14s. That doesn't really be a big difference, especially let's say it's hydrogen. Hydrogen 1, hydrogen 2, hydrogen 3. Well, hydrogen 3, called tritium, is 300 times more heavy than hydrogen 1. So that would be a big difference, okay? But we're not just grabbing 1 or 2. We're grabbing, to say we're grabbing billions or gajillions would be an understatement. We're grabbing so many that the average is working out very nicely, okay? So we got to use an average to know how much weight per particle we really have here. So on this thing, we kind of want to be able to look at this number and kind of just, well, one, calculating it would be pretty straightforward, okay? It's just an average. And if I know that if I offered anybody here in our class $50, they could come up with an average of these numbers, just plucking around their calculator for a little bit. But you should realize that your average for this guy, this is what I'm really getting at. What would be the average? I mean, you can estimate, right? I mean, it's going to be really close to 12, because there's so many 12s. And you know that there are a couple heavier versions, so it's just a little bit above 12, okay? I could guess, estimate. But at this point, it doesn't matter, and you notice that if you look on the periodic table, it's like 12.1, okay? So there's lots of 12s, okay, and not so much of the other ones. The most common isotope would be just 12. All right, so in this situation, the idea of an average would have a decimal point in it, okay? So you want to really understand the difference between what they're talking about average-wise versus a mass number, okay? Mass number measures a single atom. An average is lots of atoms. And I don't too concerned about actually calculating it, is but more that you can estimate it, okay? All right, next we got, how does an atom acquire mass? Students should be able to to model how and why different atoms of a same element have different masses. Okay, so draw a rough nuclear sketch of B10 and B11. Label the parts. Okay, so boron has 5 protons, so I'm going to go 1, 2, 3, 4, 5. And this guy also would have 1, 2, 3, 4, 5. And this guy's going to have 10 neutrons. I'm going to go zeros for that. 1, 2, 3, 4, 5. And this guy's going to have 1, 2, 3, 4, 5, 6. Now this model doesn't tell us anything about electrons traveling around the outside. So I'm not going to assume anything. Okay, and I'm just going to kind of leave them kind of as they go here, like that. Electrons around here. Right? This one I drew like an orbit. This one I drew just kind of like general negative cloud area here. Okay, so you notice here that in this case, boron isotopic pattern is they're saying, okay, there's lots of 11s and only a couple 10s. So if you find the average here on the periodic table, 10.81. Does that make sense? Okay. Now, if someone just says it's 10.81, what can you really get from that? Probably that the most common isotope is 11. Probably. But you don't know that there's even 10s available. Maybe there's only some 9s, you know, right here. You wouldn't really have anything ever in the middle here. Okay. I would say that one thing I would say that is if, yeah, this would definitely be out. Okay. But if you took an individual atom and you measure its actual mass, you might get like a 9.001 or in a 10.995. And essentially, this is using mass spectrometer, and they're just the idea of an AMU just isn't perfect. So if you see something like that, that just means 9. That just means 9, and this just means 11. Don't make it more complicated than it is. But for our purposes, typically speaking, if this was 10.995, it would just show up on the 11 line. So if you see something like a mass number that's not exactly you know, right on, you shouldn't freak out about it, but you should realize that, oh my goodness, that's awfully close. So there you go. So next, hydrogen has 3 different isotopes. Sketch them below. Okay, so we got this here. First of all, they all have 1. And if you're on your own, you're in online learning, you should be doing this on your own before I do it. Everything, if you can. Pause it, do it. Protium. Okay, so in this situation, this is going to have those guys. All right. All right. Define mass number in the small box below each name. Add the mass number of each. So this is going to be well, it's just going to be 1. Right. This guy is going to be 2, and this guy is going to be 3. Mass number. Okay. All right. Moving along. Justify or nullify the following statements. All right. 100 atoms of hydrogen have the same mass as 100 atoms of oxygen. This would be a big stinking no. Okay, you should be trying this on your own. Why? Well, hydrogen, I mean, first of all, we don't know what isotope it is. But even isotopes on average only have a mass of 1. That's the most common isotope of hydrogen because the average is 1.00. All right, and 100 of these guys, well, the 100 is oxygen. The most common form of oxygen is 16. So even if we compare these two, this is 16 times heavier than this one. Okay, so no, wrong for the student. No matter, you couldn't even get close to that. All right, 100 oxygen atoms will always have the same mass. And again, once again, the answer is no, because of the idea that we have isotopes. And sometimes oxygens can weigh 15, sometimes oxygens can weigh 16, and there are other isotopes of oxygen. I just would need to look them up. Okay? Maybe there's a 17. I don't know. The periodic table is ordered by mass. Heavy elements are at the end, lighter elements at the beginning. Okay. Once again, this is a no. They're ordered by protons, and you might find some slight variations in the weights. Typically speaking, for nuclear stability, now nuclear stability is really works off that you have these protons and you have neutrons. In in general, zero could be no charge, but I'm just going to put down uh, protons and neutrons. All right, these things are essentially glue. And for the longest time, it keeps the protons together. I mean, the protons are positive, so they're trying to, to repel each other, and they would love to repel each other in this nucleus. And this is more nuclear chemistry than anything. But you'll find, that as early on in the periodic table, it is a 1-to-1 ratio, pretty close, but not exact. But as your number of protons get larger and larger and larger, your number of neutrons required to keep stable is more. It starts to need a little more glue. So this is not necessarily guaranteed to be a straight comparison, and all of a sudden you might have a situation where the masses don't exactly match up. It's close. All right, it's close. We're ordering by protons, not just by mass. All right. Next, average atomic weight. Okay, you should be able to calculate the average of these masses, but more importantly, you should be able to estimate your average. Okay, estimate, then calculate. All right, I'm not gonna. Well, I'll just estimate here first. This thing should be. Let's see, we got here. We got 83, 40, 85, 86, 87. Now notice the slight difference there. That's a mass, okay, and that was measured by a mass spectrometer, and that's why we're getting some slight variation. Mass spec measured that, but basically this essentially is 88. This essentially is 87. This essentially is 86. Essentially is 84. So this thing is going to be really close to 88 because of the values here, but it's going to be slightly below. So I might estimate without looking at the periodic table, I might say this is going to be 87 point, I'm going to guess 8. Okay. Now, how do I calculate this? What you would do is you would take, and you could try it on your own first, okay, but you take, basically, you could use the decimal version if you want. I'm just going to use the 84. So 84 times the decimal version of the percentage would be 0.0056. Going to give you the percentage of the 84 that is 88, 84 that goes there. 86, okay, and then the fraction of that guy is 0.0986, and that is this guy. And you keep adding them up. 87 times its percentage, there we go, and then 88 times its percentage. And if you add all these up, you will just get that fraction. And I guessed 87.8. Strontium on the periodic table is 87.6. Okay, that's fine. Again, surely it's not above 88. Definitely not at 84. So it's just a smidge below 88. All right. Sample problem. A mass spec of element X is presented in the diagram above. Based on the spectrum, which of the following can be concluded about element X? Okay. Take a moment, give it a whirl. All right. Let's see what our answer is. And here we go. It says the atomic mass of X is between 90 and 92. Somewhere and that atomic mass is the average atomic mass. That's what we're looking at. That's what we're calling this. Somewhere between here is likely our average. Okay. Other things here we just don't know, right? This is a transition element. We don't know the number of protons, so we can't tell what type of element it is. We know nothing about electrons, nothing about the average atomic mass is 90. No, it's not. That's the mass number of this type of atom right there. Note the wording. All right. Can an atom change its mass? Yes, it can. So how might this happen and what might be the consequence? Okay, so this would be a nuclear reaction, and which is why we don't really do a whole bunch of this stuff. The amount of stuff that we would have in this area is very minimal, but it's definitely a very key part of chemistry. It's just not a part of this class. But you might imagine a situation where we have a ratio of protons to neutrons, and you might have technically a neutron is um, a proton and an electron squished together. Either way, so you could have a proton breaking apart and forming a neutron. You could have electron capture, where there's a couple different versions. The main one would be like alpha decay and beta decay, and there's gamma. There's just different types of decay, and I'm not too worried with it right now, and you're really not going to see as much in this class, but just realize that this is one, for example, one of more common ones, where it emits what's called an alpha particle, which is a helium particle, and this is 4 and 2, and it shoots off, um, you know, a certain number of protons and neutrons. So the answer is yes, but it would, it would be difficult and lots of energy. You're not going to accidentally have this happen. So, but one thing you might note that yes, it could, when it changes though, it could really change the identity of the atom. Okay, so it might change the actual name of the atom, like the identity. Right? Change the protons, you change the identity. All right, so here's an example of how a nuclear reaction would occur. Now notice here we have a atom of radium is breaking down to radon. Okay, and look what we got here, a whole particle. So what is this thing? Well, this thing has 2 protons, so I'm going to put it, that's the bottom number here, 2. And the mass number is everything, so it's 4. And this thing, therefore, what is this thing? It is helium. And this is alpha decay. And you'll note that in a particular nuclear reaction that 88 must equal these two. The bottom number must equal and the top numbers must equal. Okay, so 222 plus 4 should be 226. So again, not super common. All right. You want more details on isotopes and average time mass? Yeah, this is really probably the #1 topic in this thing. Here's a little video that we would use to really detail that a lot more. Take a look. All right. So now we're on our next standard. Okay, and I'm going to stop there for now, and we'll pick up a video on the second standard here, which is what protons and electrons now. So, thank you very much.